All right, let's dive in. Today, we're going to tell the story of motion itself. We're going to unlock the basic rules that control literally everything that moves in our universe, from a simple baseball to a whole galaxy. So let's get started.
I mean, really think about it. You see a car speed up, a leaf drift down from a tree, you take a walk. It all seems so different, so complex. But what if I told you it's not? What if all of that chaos follows just a handful of really simple, beautiful rules?
And that's the absolute truth of it. Looking at physics notes like these, you think motion is impossibly complicated. But it all boils down to just three core ideas, and that's the story we're going to unpack today.
Okay, so first things first. Before we can even ask why things move, we need to agree on a language to describe how they move. So we gotta build our vocabulary, starting with the absolute basics. So, our first key word is displacement. Now, this isn't just about how far you went, it's about where you are now compared to where you started. That's the critical part. Displacement is simply distance plus direction. Think of it like this. Say you go for a hike on a winding mountain trail. You might walk for 5 miles, that's your distance. But if the end of the trail is just 1 mile east of the parking lot where you started, your displacement is 1 mile east. It's the direct, as the crow flies path. And you know, this difference is a huge deal in physics. A simple number with no direction, like distance or speed, we call that a scalar. But the moment you add direction to it, like with displacement or velocity, it becomes something called a vector. And as you're about to see, adding direction changes the whole game. So we know how to talk about motion, but why do things move? Or, for that matter, why do they stay still? The answer to that question comes down to one incredibly powerful idea. And that idea is called inertia. Honestly, the best way to think about it is as an object's built-in laziness, or maybe stubbornness. It just wants to keep doing whatever it's already doing, whether that's sitting on the couch or cruising along in a straight line. And this is the heart of Newton's first law of motion. It makes perfect sense, right? A book on your table isn't going to just fly away until you pick it up. A satellite coasting through deep space is going to drift in a perfectly straight line pretty much forever, unless something gets in its way or it fires its thrusters. Things just keep on keeping on. So that something that interferes, that thing that gets in the way, it has a name. And it's basically the main character in our entire story of motion. It's the one and only agent of change, force. At its core, a force is just a push or a pull. That's it. It's what you need to overcome that lazy inertia we just talked about. See, if all the forces on something are perfectly balanced, nothing changes. But give it an unbalanced force and you will always change its motion. You'll make it accelerate. And these three laws, from the brilliant mind of Isaac Newton, they give us the whole plot. Law number 1 says things are lazy. Law number 2 tells us exactly how much of a push or pull we need to force a change. And law number 3 reveals a wild secret. Forces never act alone. They always come in pairs.
Now don't worry about the math here, just follow the logic. To figure out the total push needed to get this toy car moving, you don't just think about how fast it's accelerating. You also have to account for the force needed to beat friction. It all ties back to that one super famous equation, F equals ma. And here's that third law in action. If you push on that block with a force of 50 newtons, guess what? The block is pushing back on your hand with the exact same 50 newtons of force. You can't touch something without it touching you back. Every single interaction is a perfect two-way street.
All right, now that we have these rules down, we can start to look at more exciting stuff, like what happens when things crash into each other. This is where the laws of motion really get interesting. So one of the coolest results of Newton's laws is something called the conservation of momentum. Now, momentum is just a measure of an object's oomph, its mass times velocity. And in any collision, the total oomph you have before the crash is the exact same amount you have after. This isn't just a suggestion, it is a hard and fast rule of the universe. And this one rule explains so much. The very same math that describes a perfect collision between two balls on the left also explains the very real kickback you feel from a gun on the right. The gun has to kick backward because the universe demands that the bullet's forward momentum is perfectly balanced by the gun's backward momentum. It has to be equal. But here's a small but really important detail. Momentum is always conserved, always. But kinetic energy, that's the energy of motion, it's a little different. When two billiard balls click off each other, that's almost a perfect elastic collision, and the kinetic energy is conserved too. But a car crash? That's inelastic. The momentum is conserved, sure, but a ton of that kinetic energy gets spent on bending metal and making a horrible noise.
And that brings us perfectly to the final biggest idea in our whole story: energy. If force is what makes things change, then energy is what you have to spend to make that change happen.
So how do you transfer this energy? Well, in physics, we call that process work. It's pretty simple. Anytime you apply a force to something and it actually moves some distance, you are officially doing work. You're transferring your energy into that object.
So here's maybe the easiest way to think about it all. Imagine energy is just a kind of universal currency. If you want to change an object's motion in any way, you have to pay for it. And the way you pay is by doing work. And this all builds up to one of the most fundamental laws in all of science, the conservation of energy. So picture this ball, held up high. It's just sitting there, but it's loaded with stored or potential energy. The moment you let it go, that potential energy starts transforming into kinetic energy, the energy of motion. The ball goes faster and faster, but the total amount of energy, the potential plus the kinetic, stays exactly the same. It's a perfect one-for-one trade.
And that's our story. We started by learning the basic language of motion. Then we met the main character, force, the thing that makes change happen. And finally, we saw how it's all governed by the universal currency of energy. These three ideas are woven together, and they write the rules for absolutely everything that moves.
But that leaves us with one final, kind of mind-bending question. If energy can't be created or destroyed, if it can only change its form, then where does all the energy in the universe eventually go? What's the end game? Now that's a question that takes us right to the very edge of physics. Something to think about, isn't it?